So hello and welcome to our presentation on predicting hospital admissions based on air pollution. So this project is going to address a growing challenge, which is how pollution levels affect hospital admissions, leading to unpredictable surges that strain resources. So using machine learning, we aim to build a predictive model that's going to help hospitals anticipate these surges and manage their resources more effectively. So in this overview, I'm going to introduce the project's context, objectives, and planned approach before handing it over to my teammates, who's going to explain each stage in detail. So first of all, Ludhiana, a city in India, which is one of the most polluted cities globally, has faced deteriorating air quality in recent years. So data collected between 2017 and 2019 by the Hero DMC Heart Institute shows a strong correlation between high levels of pollutants like PM2.5, PM10, and NO2, and hospital admissions, particularly for respiratory and cardiovascular illnesses. So these surges create significant challenges for hospitals, including staffing constraints, increased costs, and reduced quality of care. So addressing this is going to require a predictive solution that bridges environmental and healthcare data. So our objective is to develop the predictive model that's going to use the pollution data to forecast hospital admissions, which is going to allow hospitals to allocate resources proactively during critical periods. So to achieve this, our work focused on aligning pollution data with hospital admissions trend, cleaning and exploring data sets to address issues like missing values, and testing and refining to produce actionable insights to resource optimization. So this concludes the overview of our pre-project work. Now my teammates will dive into the methodology, models, and results for each stage.
The first step of our project was to explore and prepare the data to ensure its quality and relevance for modeling. Two datasets. The first one, it was the pollution information, and the second one is hospital admissions. The initial exploration revealed several challenges: missing values in some columns, date format difference, and the lack of temporal alignment between the two datasets. After we applied rigorous data cleaning, columns with a fill rate of less than 80% were removed, which reduced noise and kept only essential information. To better understand the relationship between pollution and hospital admissions, we generate exploratory visualization. And we can see that the pollution spikes are followed by an increase in hospital admissions. After preparing the data, we implement two standard models, the decision tree and the KNN. To ensure a rigorous evaluation, we split the data into two sets, 80% for training and 20% for testing. The variables were normalized using standard scalar to avoid scale difference influencing the results. And you can see that both models were trained and evaluated using the following metrics: MSE and R squared. For the decision tree, we have a R squared of minus 0.2, which means that the model does not explain the variations in admissions better than the mean of the data itself. The model is therefore poorly adapted to this dataset. And for the KNN, we have only 17% of the variations, which is explained. These models remains underperforming with a low R squared. The results show that the KNN models outperforms the decision tree in terms of accuracy, lower MSE, and ability to explain data variations. However, this performance remained limited and justified the exploration of more complex models to capture temporal and non-linear relationships between variables.
Okay, so for the stage 2 of our project, the goal was to improve the performance of the baseline models introduced in the first stage. We focused on three machine learning algorithms that are decision tree regressor, KNN, and the gradient boosting. To optimize the models, we applied the grid search CV to systematically tune hyperparameters. For instance, we determined the optimal maximum depth for decision tree and the ideal number of neighbor for KNN. This configuration were validated using the cross validation. So the performance of the models they are here. There was evaluation using the two key metrics, so the MSE and the R-square. Both decision tree and the KNN, they showed similar results, with MSA around 62 and R-square score of 0.16, indicating limited predictive ability. In contrast, the gradient boost model achieved significantly better performance with an MSE of 55.48 and an R-square of 0.26, demonstrating its ability to capture more complex pattern in the data. And here we also see the best parameters that we found for our three models.
In stage 3 of our project, we focused on implementing an alternative advanced machine learning model to predict hospital admissions. In this case, we decided to use convolutional neural networks. First, the data was prepared by merging hospital admissions with daily pollution metrics, along with temporal features. The neural network model was designed to capture patterns in the time series data using convolutional layers, while integrating numerical and categorical features through dense layers and embedding techniques. Dropout layers and max pooling were also included to reduce overfitting. The results showed that the neural network achieved the lowest mean squared error and root mean squared error, making it the most accurate model overall. Gradient boosting closely followed, delivering strong generalization and the highest R-squared score. In comparison, simpler models like decision tree and k-nearest neighbor struggled, showing significantly higher errors and negative R-squared values. While the neural network's complexity helped it stand out, its performance being slightly ahead of gradient boosting suggests some mild overfitting, despite using regularization techniques. In conclusion, this stage demonstrated the value of advanced models like neural networks and gradient boosting in handling complex datasets, providing significantly better predictions than traditional models.